Hey, hello, and welcome back, everyone. So we're moving on to the very last subsection of this chapter, and it's really the second half to that section called asymptotics. So let's recall what we had with asymptotics. Or really asymptote. It's the adjective of asymptote. We had equilibrium, and now we have blow up. And these are going to directly correspond to whether or not solutions to dynamics have horizontal asymptotes. In the case of equilibria, and in the case of blow up, we're looking for when solutions to dynamics have vertical asymptotes. And if we think about what this might mean, I'm going to give myself a plot over here and assume this is the time axis. So as I move to the right, time moves forward, and suppose whatever I'm measuring is a function of time. Suppose that, I'm measuring something blah, 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 but then it reaches a vertical asymptote, maybe at t equals tb, for example, for blow up. Let's think about what this is actually saying about my quantity. So I'm measuring a quantity, and my measurement, it's moving along just fine from its initial condition, but eventually the measurement value gets higher and higher and higher, and if I truly reach a vertical asymptote, it's saying I'm performing a measurement value which equals plus or minus infinity at some finite future time. Right? This is a finite number in the future. It could be 8 days from now, it could be 45 minutes from now, whatever it is. It's some finite future time, and the measurement I was performing all of a sudden reaches infinity. Hopefully with an explanation like that, it makes sense why we use the word blow up, because what's actually happening to our measurement, it is blowing up. And in fact, we'll often call it finite time blow up as well, because the amount of time we've waited before it blew up is a finite amount of time. Okay, so that's what we're going to be studying today, as opposed to our horizontal asymptotes. And I do have my definition here, which we just kind of described. So there, we say that the solution y of t exhibits blow up, or finite time blow up, if there is some time. Of course, it has to occur after the initial condition. If my solution says it occurs in the past, we kind of just pretend it didn't actually exist in the past. So it needs to occur in the future. And at that time, what we're saying is that the solution to our measurement, if we perform the limit as time approaches that point, TB, and of course remember that upper superscript minus just means from the left or from below. We're not going to look even farther ahead into the future. We approach the future from the present, and that's it. You can't approach the future from extra future. So it approaches TB, this blow-up time, from the left, and we assume that it equals plus or minus infinity, or that's what it needs to satisfy to be called a blow-up. Equivalently, we'll say that it achieves a blow-up if the graph achieves a vertical asymptote, like I already kind of described, and in particular, T sub b is called the blow-up time. We can do something similar with discrete dynamics. It doesn't make quite as much sense, because if we plot discrete dynamics, right, plotting them just occurs as these steps, and there's no notion of a vertical asymptote for sequences. If there were a vertical asymptote, or the closest thing you can think, if you were connecting the dots, so to speak, a vertical asymptote, you would have to connect to a dot at plus or minus infinity. Like this next dot would have to sit at negative infinity for us to connect there. So the best thing we can do is we can say that there's a point at which the solution is undefined, in the sense of divides by 0. Equivalently, y and b divides by 0. Okay, so we'd be looking for times when our solution divides by 0, perhaps. So that's what we would say in the sequence world, or the discrete world. It tends not to be as big of an issue with regards to sequences. We don't really work with blow-up times on sequences quite as often, although I will provide an example just so that you can see what it would look like. Let's look at a case where we have an initial value problem for integrals, and let's give ourselves the initial value problem. Y prime is secant squared after the initial time of pi, and let's suppose that at the initial time we are equal to pi. We of course can solve this, right? The solution to an IVP for integrals is going to be the initial value, which in this case is pi, plus the integral, which starts at the initial time, pi, and ends at the future time, t. And we're going to grab the function on the right-hand side, secant squared, and we're going to change its variable to s. So that's going to be our solution. Now we're going to compute. Well, how do we compute the antiderivative of secant squared? This is actually a pretty classic one, because if we remember the derivative maybe of tangent, you can get there using the quotient rule on sine over cosine if you want to, or you can just memorize it as the derivative of tangent. One way or the other, you end up with secant squared as the derivative of tangent. So the antiderivative of secant squared is just tangent. You plug in your bounds t and pi, we end up with tangent of t minus tangent of pi, but recall that tangent of pi is going to be just 0. So we end up with pi plus tangent of t as our solution to this initial value problem. We then ask, if we're looking for a blow-up time, does there exist a time, and we should really think a first time, after the initial time, which in this case was pi. You can find the initial time right there. So does there exist a time after pi for which the limit as t goes to this time, tb, of pi plus tangent of t equals plus or minus infinity? Question mark. And an easier way to answer this is really, we're going to ask the question, is there a time at which our solution divides by 0? That's almost always going to be the way to answer these problems. So to find a blow-up time, we're looking for our solution dividing by 0. Written as tangent, it doesn't look like it really divides by 0 ever, but we're going to recall that tangent is really sine divided by cosine, and so dividing by 0 is equivalently asking, when is cosine of t equal to 0? So that's what we're going to be focused on solving. Lots of ways to think about when cosine of t is equal to 0. Let's think about the unit circle, and let's think about cosine is going to be the values of x on the unit circle. So when is x 0? X is 0 at the top and at the bottom. So this would be when cosine is 0 as well. What are those angle measurements? Well, that's an angle of pi over 2. And if we continue around, this would be 3 pi over 2. So we've got a couple choices here. And of course, we can add 2 pi or subtract 2 pi from either of these numbers. But in particular, we're asking for the first time greater than our initial time, and our initial time was pi here, right? So the first of these two numbers that occurs after pi, let's recall pi ends up over here, that's a rotation by pi. First of these numbers occurring after pi is going to be 3 pi over 2. And so we can say that 3 pi over 2 is the first time we divide by 0, and equivalently, it is the blow-up time. So our second problem is going to be the blow-up time for an IVP for sums. And like I said, these are uncommon, but we can still technically define them, and so I wanted to go through a definition for it. So here's our IVP for sums, and we're going to want to solve this with, well, yn is always going to be equal to its initial value, which is 0, plus the sum k starting at the initial time, which is 0, and it's going to end at n minus 1. And that summation is going to occur over the right-hand side of the derivative term. So that's going to be k squared plus 9k plus 20, all divided by k squared minus 9k plus 20. And so that's our solution. We could do our best to actually compute this in closed form, but we're going to have a pretty tricky time of that. And so what we're going to do instead of trying to compute it in closed form is we're simply going to ask, well, if yn equals this, and we can interpret this as a summation of, well, plugging in zeros, 9 times 0 plus 20, all over 0 squared minus 9 times 0 plus 20, and then we'll add 1 squared plus 9 times 1 plus 20, all over 1 squared plus 9 times 1 plus 20, that's minus, plus 2 squared plus 9 times 2 plus 20, all over 2 squared minus 9 times 2 plus 20, plus dot 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 plus, where does this end? Well, it ends at k being n minus 1, so it's end at n minus 1 squared plus 9 times n minus 1 plus 20, all over n minus 1 squared minus 9 times n minus 1 plus 20. Okay, so it eventually terminates at, some polynomial evaluation of this upper term, but you could imagine if any term divides by 0, then we blow up. Right? If any one of these terms is going to end up dividing by 0, we will achieve blow up because, you add a bunch of finite numbers together and eventually a division by 0, yeah, you're going to be undefined. And so we're simply asking for, when is the first case when a term divides by 0? One of these terms. When's the first case when one of those terms is going to divide by 0? We can get there basically by evaluating the denominator. That's the term we care about, right? So we evaluate that denominator and we say, that's a quadratic. I can figure out when quadratics are 0. I could use the quadratic formula if I want to. Or I could simply factor it. Factoring tends to be easier. If you can see it happen pretty quick, it's good. But if you can't see it happen, then normally use the quadratic formula and figure out when the quadratic is going to be equal to 0. Well, in this case, it says I'm equal to 0 when k is 4 or k is 5, of which the first value of k, when I divide by 0, is at k equals 4. Okay, it's the smaller of the two numbers, k equals 4. So the question is, at what value of n will there be at least one term which includes k equals 4? Well, it's going to be exactly when the upper bound is 4. That'll be the first case when k is equal to 4. Well, the upper bound happens to be n minus 1. So what does that say about n? So n happens to be 5. So since we notice that n being 5 is going to be the first time that we divide by 0 in one of our terms, we can say that the blow-up time is 5. We've also got an example of a blow-up for a separable ODE. We're getting practice with all of our dynamics here. So here's a separable ODE. And if we want to solve our separable ODE, we can do our step-by-step method, which basically says in the first step, I'm replacing y prime with dy dt, and I'm replacing y of t with just y. And then I'm going to solve for every term with a y on the left, which means I'm going to divide both sides by y to get 1 over y dy. And I'm going to solve for every term with a t on the right, so I'll end up with 1 over t minus 1 squared dt. And what is that going to give me if I go ahead and integrate both sides here? Well, integral of 1 over y is going to be the natural log of y. The integral of 1 over t minus 1 squared will be a negative 1 over t minus 1. This is really coming from me recognizing 1 over t minus 1 squared is 1 over, actually it's t minus 1 to the negative 2 power, or equivalently even with a u substitution, u to the negative 2 power. So if I use the power rule on u to the negative 2, that's going to give me negative u to the negative 1, or negative 1 over u, or negative 1 over t minus 1. Okay, so that's going to be the solution up to the initial value. So now we have to find c according to the initial value, which means I'm going to plug in a 1 for y. So this y will be replaced with a 1. And I'm going to plug in a 0 for t. And so this t is going to become 0. And we find out that, well, log of 1 is 0, and negative 1 over 0 minus 1 is a positive 1. So this tells me that c will be negative 1. So now that we know c is negative 1, I go ahead and include c as negative 1 in my solution. That's going to give me that the solution is log y is negative 1 over t minus 1, minus 1. Or if I solve for y, the real solution, taking the exponential of both sides, e to the negative 1 over t minus 1, minus 1. If I want to perform a little bit of simplification in this numerator here, I can go through common denominator process. That ends up with e to the t over 1 minus t. So here my solution is going to be e to the t over 1 minus t. As always, if we're searching for a blow-up time, we're going to say, well, technically it's the time at which if I take a limit, then I achieve the value plus or minus infinity. But let's be honest, it's always the same to find these. We're asking about dividing by 0. Okay, where's the denominator in this problem? It's right here. So when does denominator equal 0? Big question mark. Well, the denominator is 1 minus t. When is that 0? That's going to be 0 at t equals 1. And so we say the blow-up time is 1. We have one final example with regards to actually finding these. We've got some future work later in this section, but one final example with regards to finding blow-up times, which is a very nice applied example. So let's say we want to escape a black hole. The physics department has gone ahead and developed a model for gravitational acceleration near a black hole. They found out that the velocity of a spaceship pointed directly away from the singularity of the black hole. The change in velocity, also known as acceleration, because that's how gravity affects things, it accelerates things. So the acceleration ends up being equal to 1 divided by this x, absolute value of x. This is going to be some initial position from the black hole, or distance from the black hole, plus the initial velocity, v0, minus the speed of light, c. That entire v0 minus c is multiplied by time, and then the entire denominator ends up being squared. Okay, so that's how the acceleration is affected, and my initial velocity is just some number v0. What the physics department has asked us for is to find the smallest initial velocity for which the spaceship will be able to escape the gravitational pull of the black hole. In other words, what would the acceleration be at the singularity? Well, it would be infinite. It's asking us to avoid a blow-up time. In other words, we can interpret this as saying, what do we need v0 to be to avoid falling in the black hole? Because nobody wants to fall in the black hole. So we're going to have to go ahead and solve this initial value problem. Now, it's an initial value problem for integrals, so our life shouldn't be too terribly hard. What's the solution going to look like? Well, v of t is going to be my initial value plus the integral from the initial time 0 to the current time t. of the function on the right-hand side, but I'm going to swap out my variable for s. 1 divided by absolute value x plus v0 minus c s squared ds. And then I have to actually compute that integral. It's not too hard to compute. I've gone ahead and gone through the u substitution for it. I'm going to name the entire term in parentheses in the denominator, except for the square. That's going to be my variable u. Okay, so I'm going to perform a little bit of u substitution with that. If I say u is absolute x plus v0 minus c. Now keep in mind that s is the variable that I'm actually integrating over. So when I take a derivative to find du, I'm taking a derivative in the s variable, okay, of u. ds, and taking a derivative in the s variable. So of all of that in the s variable, I'm only going to pick up the coefficient on s, which is v0 minus c ds. And so if I rearrange this equation for ds, we find out that ds is equal to du divided by v0 minus c. So that's where du divided by v0 minus c comes from. If I go through the work of finding my new bounds, u max will occur at s max, which will be when s is equal to t. So there's u max. That's why I've plugged in u max up there. And u min will occur at the lower bounds. If I plug a 0 in here, that term falls out and I just have absolute x. And so that's why I have absolute x there. So that's me going through the work of u sub, and then if I look at this 1 over u squared, that's u to the minus 2 power. So really I'm doing the power rule on that, which will be u to the minus 1 divided by negative 1, also known as negative 1 divided by u. So that's why I have a negative 1 divided by u as my antiderivative. Then I'm going to plug in my upper bound for u and then subtract my lower bound for u. We end up here. And if I simplify this a little bit, you know, it does not look good, but no one said that spaceship travel away from a black hole should look good. This ends up being the equation we have. So the big question to say, if we never want to fall into the black hole, does this solution ever exhibit blow up? We have to figure out the question of, well, we've got a couple denominators here, 2 denominators, but this second denominator, notice that there's no t in here. Okay, so if that denominator doesn't divide by 0 right away, it doesn't matter what the value of t is, how far in the future I move, that second denominator is never going to divide by 0. And so this first denominator is the one that I really care about. The question is, for which value t, which t makes this divide by 0? And the answer is going to come by just grabbing that and setting it equal to 0. So I'm going to grab this denominator and I'm going to set it equal to 0. When I do that, if I want to solve for t, what do? Well, I pull this to the right-hand side. We end up here, and I'm going to divide both sides by v0 minus c squared. That's going to cancel on the left, divided by v0 minus c squared on the right. We end up with t, or our blow-up time, is x divided by c minus v0. So it's the distance I started from the black hole divided by the speed of light minus my initial condition, my initial velocity. So to answer the question, does this occur in the future, right? This is the blow-up time. But is it in the future? We're asking for when this blow-up time is positive, when it occurs after my initial time. Well, it's going to be positive. The numerator is always positive. It's an absolute value, so it had better always be positive. My denominator will be positive when c minus v0 is positive, or if I add v0 to both sides, we find out that our initial velocity is less than the speed of light. Okay, so that means we do have blow up. We do have blow up, also known as reach the black hole, get sucked into the black hole, when the initial velocity is less than the speed of light. Which means to escape the black hole, if I want to escape the black hole, our initial speed must be traveling at least at the speed of light. It's got to be greater than the speed of light if we want to escape. So that's impossible, which means good luck escaping the pull of a black hole. Now there's lots of physics assumptions to make here because black holes only have finitely lived lifespans and some other things that are going on behind the scenes. But you could imagine if black holes had infinite lifespans and we didn't have the acceleration of the universe itself due to dark energy, black holes would eventually gravitationally dominate the universe, and all of us, even the Earth, etc., would eventually get sucked into a black hole. So there's lots of assumptions to be made here, but it is giving the right answer underneath all of those assumptions, which is to say you're never going to escape a black hole. I mean, you may postpone your demise by a considerable amount of time, but you'll never escape it. You may die for other reasons first. Okay, so that's really getting through blow up, and we're going to move on to a second part of kind of the ideas of blow up, which some of you who've been paying attention now may have noticed and have questions about. If we look at the previous examples, the equations we were solving, the first example, we had y prime was secant squared, which is equivalently 1 over cosine squared. Our second one, we had the finite difference of y, was this ratio that we were able to factor. In the third case, we had y prime was y divided by t minus 1 squared. In the last case, we had this acceleration, which was 1 over absolute x plus v0 minus c times t squared. And if you look at the blow-up times we achieved, the blow-up time in the first case was actually a time when the denominator on the derivative became 0. In the second case, it was when the denominator on the derivative became 0. In the third case, it was when the denominator in the derivative became 0. And in the last case, it's a little harder to see, but it's also when the denominator in the derivative became 0. So a good question to ask is, did we actually need to solve the IVP when we could have just looked at the denominator in the derivative for each of the cases above? And the answer ends up being yes, you do still have to solve the IVP, because sometimes, even though the denominator in the derivative is 0, we actually don't have blow-up. Okay, so it's a little counterintuitive that the derivative's denominators could become 0 in some cases. It didn't happen so far in these examples, but in the future we could see a case, and actually that is my next case, where the denominator of the derivative does become 0, but the solution to the dynamics doesn't actually exhibit blowup. And so here in this example, I've labeled it the integrable singularity. That's what we call it, because dividing by 0 will produce a singularity for us. But the fact that it's integrable means that if you integrate it, if you get rid of this derivative, in fact the singularity disappears as well. And so that's just something we need to keep in mind, and it means that we can't get away with just finding out when the derivative has a denominator equal to 0. You actually have to solve the dynamics and then figure out where you divide by 0 to calculate blowup. Anyway, let's look at this initial value problem for integrals given by y prime is equal to t minus 1 over t squared minus 2t plus 1 to the 2/3. And let's go ahead and solve it. Its solution is going to be the initial value, which is 0, plus the integral of the initial time, which is also 0, up to the current time t, s minus 1 divided by s squared minus 2s plus 1 to the 2/3 power ds. And then we just have to compute this integral. If we go ahead and compute the integral, we're going to do this by u substitution, because my denominator certainly has a function in parentheses. We're going to name that entire term in parentheses in the denominator u. Let's compute its derivative really quick. The derivative of s squared is 2s minus the derivative of 2s will be minus 2. The derivative of 1 will be 0. And so we have 2s minus 2 ds is equal to du, or in other words, s minus 1 ds, and that's really our numerator ds. S minus 1 ds is equal to 1/2 du. And so we replace s minus 1 ds with 1/2 du. And now we have an integral. I've replaced my bounds there as well. An integral just in the variable u. It looks like a power rule. The integral of u to the minus 2/3 is going to be u to the negative 2/3 plus 1, all divided by negative 2/3 plus 1. That ends up being what? U to the 1/3 divided by 1/3, also known as 3 u to the 1/3. And so we see a 3 u to the 1/3 show up here, u being the entire denominator, t squared minus 2t plus 1 when I evaluate at t, and then if I subtract off evaluating it at 0, t squared minus 2t plus 1, or 0 squared minus 2, 0 plus 1 is just going to be 1, so I subtract 3/2. Okay, so this is now going to be my solution. And if we go ahead and plot the solution, and you could probably see it from just looking at it, does this divide by 0? And the answer is certainly not. There's no division by 0 here. And if we plot it, we see the plot given here where there's definitely a cusp, so something happened at one point in time, but we never divided by 0. And if we go back to the initial value problem, our derivative does divide by 0 when t is equal to 1. And so there's these cases where, yeah, even though the derivative divides by 0, the solution does not. And so blowup can or cannot happen depending on how strong of a division by 0 you have in your derivative terms. It just so happens the earlier derivatives we saw in this section were strong enough. So in combination of this remark, in the example, I'm bringing up the final topic of today, which is one more version of improper integrals. So we had improper integrals of the form like negative infinity to infinity f of x dx before. Maybe you just put an infinity on one side before. And actually, I didn't say this in the video, but it was listed in the video. I had called these two type 1 They're improper integrals of type 1, and those are the improper integrals when the bounds reach an infinity, so like horizontal asymptote improper integrals. Now we're going to see that we can define improper integrals, what I'm calling of type 2, where f of x divides by 0 somewhere within the bounds from x min to x max, right? There might be a place within the integral itself. You can imagine if I have a plot here and I have my function, suppose it divides by 0, I have some asymptote right here because I've divided by 0, but maybe I still want to compute the area which includes that dividing by 0 region. Right, so how do I define an integral over a region where the integrand or the function inside of the integral divides by 0? And the way this is going to work is we're going to establish the point that the function divides by 0. We're going to give that point a special name. So we're going to say if f of x star divides by 0, then what do? Well, we take our original integral and we break it up. We break up the original integral at x star. And so there's some point in my domain that I'm dividing by 0. I don't know how to compute the integral over the entire range anymore. I mean, you would be tempted to just do capital F of x max minus capital F of x min, but it's not actually allowed because you've divided by 0 in that range. So what you have to do instead is you do capital F x max to the special point where you divide by 0, and then you have to add a second integral from x min to that point where you divide by 0. And in fact, because f of x is undefined here, as in we've divided by 0 there, you have to take limits, right? These are going to be vertical asymptotes. You're going to be required to take limits at each of these points, x star as well as x min and x max. Just as before, if the limit of an improper integral exists, we're going to call it convergent, and if the limit of an improper integral doesn't exist, we're going to call it divergent. So this definition is maybe a little bit abstract. It makes a lot more sense when you see it in person. Let's just consider this first example I have here. Suppose I wanted to integrate from 0 to 4 a function like x divided by x squared minus 9 to the 1/3 power. The first thing we ask when we see a denominator is, does this divide by 0 over the interval? What is my interval? It's 0 to 4, right? There's a 0 and there's a 4. So we ask that question, and especially if we factor that denominator, but even if we didn't, you should be able to tell that x squared minus 9 is equal to 0 when x is equal to 3. Or in fact, in this case, I'm going to give it that little star. So there's a very special point in the range 0 to 4 where it divides by 0. That special point is 3. And so what do I have to do with improper integrals? It says instead of computing the integral from 0 to 4, you actually compute the integral from 3 to 4 and from 0 to 3. This may seem like it does nothing, and sometimes it doesn't. Sometimes it's true that it does nothing, but other times it's important. Okay, you're going to run into problems if you don't do this every time you're working with an improper integral of type 2. And so we have to split this up at 3 because our denominator divides by 0 at 3. And then we're just going to compute each one individually. We're going to compute, this is me computing the left-hand integral plus me computing the right-hand integral. Now to compute those integrals, it's really not bad because I'm still just going to calculate the antiderivative, right, or the improper integral. So I'm just going to compute capital F, which is the antiderivative here. This ends up being a u substitution as well, with in particular u is x squared minus 9. So then du is 2x dx, rather 1/2. Du is x dx, and here's my x dx. There's my 1/2 du. And I just go through the power rule and I end up with 3/4 x squared minus 9 to the 2/3 plus c as my antiderivative. And then I'm going to have to compute limits as x approaches certain values of this answer. So I'm going to compute the limit as x goes to 4. Well, that's going to be, what, 16 minus 9. I'm going to compute the limit as x goes to 3. That's going to be 9 minus 9. The limit as x goes to 3 is going to be 9 minus 9. And the limit as x goes to 0 is going to be 0 minus 9. If I go ahead and write those all out, I get some zeros in the middle. I get 7 to the 2/3 and negative 9 to the 2/3. Those really can't be simplified too much. We end up with 3/4, 7 to the 2/3 minus 9 to the 2/3. If you really want a value for that, it's about negative 1/2. Okay, and since this existed, right, since we got a final answer here, we say that the improper integral converges. We have another example here where we're going to compute the integral from -1 to 1 of 1 over x dx, and you'll see here why we actually do have to go through the work of splitting this up where we divide by 0, because let's just say, let's pretend we take the naive approach, where the antiderivative is log of absolute value x, and then we're going to go from -1 to 1. We're going to plug in log of 1 minus log absolute value of -1. These both end up being 0, and so the naive approach is telling us that the area under that curve is equal to 0, but it's not, because if I look at the curve, the curve achieves a value of positive infinity. It does achieve a value of negative infinity, and there is a way to interpret it. It's called the Cauchy principal value, a way to interpret that 0 as the two areas canceling out. But in some sense, an area equaling infinity, you can't really take infinity minus infinity and pretend like it's always equal to 0, because there are situations where it's equal to 5, and where it's equal to -9, and where it's equal to 276.3. So you can't always do that, which means that, we do have to split this up at 0 to give ourselves an actual answer here. So we're going to go ahead and ask, where in the interval does this divide by 0, which of course is at 0, which means we're going to split the integral up into two integrals individually, where they've both been split at 0, and then we're going to compute the antiderivative, which is still log of absolute value of x, and we're going to evaluate a few limits. If we evaluate the limit as x goes to 1, we have log of 1. As x goes to 0, look at that, we have an infinity. As x goes to 0, look at that, we have another infinity. And as x goes to -1, we'll have log of -1. And so the fact that two of these limits, not even one of them, but two of them had infinities, we just say the improper integral diverges. There's no answer to this improper integral, it just diverges. If you want to give that answer 0, spend 5 more years in math and figure out what the Cauchy principal value means. Otherwise, you have to tell me that it diverges. We've got one more example here. We're going to compute the integral from -pi/2 to pi/2 of tangent plus cotangent. And keep in mind how we actually want to integrate both of these. Tangent's going to be sine over cosine. Cotangent's going to be cosine over sine. Big question is, do we divide by 0 within the range -pi/2 to +pi/2? Well, does cosine of x ever equal 0 within that range? Let's think about cosine with regards to the unit circle. Cosine is the x value. When is the x value equal to 0? Well, it's up here and down here. Down there is at -pi/2, and up top is at pi/2. So not really. Don't have to worry about cosine. Does sine ever equal 0? Yeah, sine is definitely equal to 0 right here at a value of x being equal to 0. So because sine of x equals 0 when x equals 0, we have to divide, or really split up, this integral at the point 0. So we go ahead and split the integral at 0, and then we're just going to go ahead and compute the limits as x approaches all 4 points, the 2 boundary points, as well as 2 copies of 0, and we're going to see what we get. To see that, we're going to need to know capital F, so we're going to spend some time computing capital F. In this case, capital F is going to be the indefinite integral of tangent plus cotangent, or sine over cosine plus cosine over sine. We're going to do a couple u substitutions here. So I'm going to let u be cosine, and I'm going to let v be sine. And then, well, the derivative of cosine is negative sine, right? So we're going to have to pay the price of a -1 on the first term. The derivative of sine is just cosine, and so we just have a 1 in the second term. Both of these are going to turn into the natural log and the natural log. So there's my natural log of u and natural log of v, or in other words, negative natural log cosine plus natural log of sine. And if I want to use some log rules, I can combine those and say this is the natural log of sine divided by cosine, or natural log of tangent. And so the natural log of tangent is going to be my capital F that I'm going to compute 4 limits on, natural log of tangent. And so over here, I go ahead and compute limits on the natural log of tangent in 4 cases. When you let tangent be pi/2, you find out that tangent is equal to infinity there, and the logarithm of infinity is infinity. When you take tangent at 0, you find out that it's equal to 0, but the logarithm of 0 is minus infinity. Tangent at 0 is still a logarithm at 0, so you're going to get minus infinity, and then tangent at -pi/2 is actually negative infinity, so the logarithm of absolute value of negative infinity is going to be positive infinity, so you're going to get one more copy of infinity here. And so we get, even if one of these ended up being infinite, we ended up getting 4 infinities, but the fact that one of them were infinite means that we're going to say that the improper integral diverges. So in some cases it converges, in other cases it diverges. And we just want to mention, this is how we're going to finish the entire chapter, the following statement. Therefore, dynamics may involve division by 0, and these cases may result in blowup when an improper integral diverges, or may not when an improper interval converges. And it is up to us to determine which is the case, and hence determine the future and or validity of our models. Anyway, I'll see you in the next video.